Okay, let's look at a steady state isentropic device and see its efficiency and see how that affects its actual performance. So we have a turbine, and as a reminder, a turbine is a device that does work for us, okay? It produces work by flowing some sort of a gas through it, and as the gas is expanding through the turbine, it moves some sort of rotor or some sort of blade, and it does work for us. So it's going to output this much work as a result of the gas expansion within it. And we know that the isentropic efficiency is 88%. And we want to know four things. We want to know the actual temperature of the outside of the turbine. We want to know the ideal temperature, meaning at isentropic conditions, meaning when everything is reversible, sort of the attainable, not the attainable temperature, but the cap, the limit temperature that we're going to get. Okay, so it's going to be the lowest possible temperature at the end of it. We want to know the outgoing pressure as well as the entropy generation, which again is just sigma. Okay, so before we do anything, let's make assumptions. So assumptions. Okay, whenever you have a gas that's not tabulated, it's really good bet. It's a really, really good bet to assume it's ideal. So assume this thing is ideal gas, which pretty much is. We'll act that way. You're going to also assume that since we're not really discussing much of a kinetic energy, or there could be kinetic energy difference, we will assume that there's going to be no kinetic energy, no potential energy, and this thing is also adiabatic. Okay. So what we're going to do now is look at the first law of thermodynamics. Then we're going to eventually look at the second law of thermodynamics to get the entropy generation. The reason I'm looking at the first law of thermodynamics is because it's going to give me information for the temperature. So I know that when I'm looking at the adiabatic, the isentropic efficiency of a turbine, it's basically what I want divided by what I could have, right? So what I'm going to actually get, the actual work, okay, is divided then by the isentropic work. And this thing is equal to 88%, so 0.88. So I have a ratio. So if I can get this idealized amount of work multiplied by 0.88, I will be able to get my actual work. Okay, so if I'm looking at the first law of thermo, and I'm going to say, so let's look at first law and let's do one inlet, one outlet, because that's kind of like what it looks like here. So we have du dt is going to be equal to Q minus W minus the delta H minus the delta KE minus the delta PE. We just got done saying that this goes away and this goes away. There's no Q and there is no W. This thing is at steady state. I should have said that here, not the assumption, SS in steady state. This is 0. So what we're getting is that the work, oops, I'm sorry, the work is not 0. Mistake. This work is definitely not 0. We're basically solving it. What we're getting here is that the work, negative work, is equal to the delta H. And for an ideal gas, negative work is Cp dt integral. Okay, this way. All right. So what I will do is I will make the assumption that Cp is temperature invariant. Now, I don't have to if I have Cp data for air, but I will. So I'm going to go to the back of the book. And in the back of the book, you have information here for specific heats. I'm looking to show you here. So 0 pressure specific heats for 6 common gases. And so we have air, carbon dioxide, carbon monoxide, hydrogen, nitrogen, oxygen. So I'm going to look at air, and I'm going to look somewhere around the vicinity of where I want to be. So I have the CP value here, I have the CV values here, and I have the K. K is obviously just these two divided. So that's fine. So we're going to look at that. And from that table, I just kind of fished out the CP. And the CP is given to me as 1.14. So when you CP is 1.14 joule per gram Kelvin. Okay. All right. So what we're going to do is we are given the work, and so we could put that in here and get the temperature. Okay, so I'm gonna integrate this by taking CP to be constant, and I will get I'm gonna bring it down here. Negative W is equal to CP T2 actual minus the initial temperature. Okay, so the initial temperature is given to me in the problem to be 1,000, and this is 1,000 no matter if this is isentropic or not. So I know that this is 1,000. I know this is 1.14, and I know the work here is given to me as 235.7 joules per gram. So I'm going to put it all in. Negative 235.7 joule per gram is equal to 1.14 joule per gram Kelvin. T2A, I don't have that. I'm going to solve for that. Minus 1,000 Kelvin. And therefore, when you solve this, you find, this is just one equation, one unknown, easy peasy. This is 793.6 Kelvin. Okay, so that answers the actual temperature. We want to know the actual temperature at the end of it. Okay. Now, to find so this is work actual. To find the isentropic temperature, T2S, what I need to do is use exactly the same equation, okay, but use the isentropic work. Okay, so T2S minus T1, we're going to assume it's starting at the same temperature. Now, this thing here, how are we going to get that? Well, it's from here. We know it's the actual work is equal to 0.88 dat, meaning that the amount of work we get out of an isentropic process is higher than the amount of work that we're getting from an actual process. So it's going to be work actual divided by 0.88, right? If I solve it here, work S is equal to work actual divided by 0.88, which is, what the heck is this? 235.7 divided by 0.88. Okay, and it's 267.8 joule per gram. So we're going to use this here. Okay, so now negative 267.8 joule per gram is 1.14 joule per gram Kelvin. T2S, because this is the isentropic final temperature, minus 1,000 Kelvin, and we get that T2S is lower. It's the lowest possible temperature we could potentially get. We will never go that low, but that means that our process is not that far off. We know it's about 88%, so it's operating at a pretty good efficiency. So we're going to get at a slightly higher temperature than what we could ideally get. All right. Now we are asked for the outgoing pressure. So when we discuss turbines and most devices, we're going to make this assumption at the end, either the beginning or the end should be the same. So I'm going to draw here a Moliere diagram like a sketch. I have H versus S bar. And I'm going to have two isobars, P1, and I have P2. Okay. And what we're going to do is, I just have two isobars. Actually, the first isobar is not even that important. What we're going to do is we're going to have a pressure. Okay. We're going to have a starting point at P1. And we're going to go to P2 no matter what. So we have two possible routes. Either we go down an isentrope, meaning S is remaining constant, some sort of S. This is going to be an isentropic process. Or we're going to go some other non-reversible way, in which case S changed. But no matter what happens, we have P1 and P2 to be equal. So not be equal, sorry, P2 to be equal for both processes. So we know that P2 actual is equal to P2 for the isentrope. We also know that P1 is P1 is P1. We're not really changing it. It's the beginning. It's the same state at the beginning. Okay. So what we need to do is just evaluate the isentropic pressure, and that will give us the outgoing pressure. So it's an important thing to understand here that you don't have to evaluate two separate pressures here. You do have to evaluate two separate temperatures. You don't have to evaluate two separate pressures, okay? Because pressure, as a reminder, is not a metric for irreversibility for a turbine, whereas a turbine is the turbine is the temperature is what's really dictating if something is going to be isentropic or not. And as a reminder to show you that, if you look back at the equations that we had describing the efficiency of a turbine, and we're going to use the hydraulic just to make that point, but this is not hydraulic here. This is non-hydraulic, this is air. But just for a hydraulic type thing, just to show you what happens, we showed in the notes, we showed that Cp delta T plus V delta P is the non-ideal, the real, quote unquote, the actual process, whereas the isentropic process is just V delta P, meaning that since this is isentropic, this is not, these two are the same. Delta P will remain the same. It's just that delta T will be different for an actual process. And so we're going to use delta T as a way to determine how much irreversibility there is in the system. That's what we were saying. And so that's why we had two different two different delta T's here. We have a lower delta T here and a higher delta T. We're going to have, we have a lower delta T here. We have a higher delta T here. This then tells me that I have more irreversibility in this system than in this system. Okay, so we're gonna use, since T1 is the same no matter what, it's 1000 Kelvin. T2 is really going to tell me how irreversible this is. Okay, so this is definitely going to be an irreversible process for the actual thing. Okay, anyway, we don't need this equation. I just want to show you where this came from. We don't even need this. I just want to, again, cement that we don't have two different pressures to evaluate, just the one. Okay, so we're going to look at the isentropic condition, and it gives us an equation between the temperatures and the pressures for an ideal gas. So for an ideal gas, isentropic, so it's not, we're not making any new assumptions. We said it's ideal gas. We know it's isentropic for the reversible process. We know that T2 over T1 is equal to T2 over T1 raised to the K minus K1 is going to be equal to P2 over P1. And again, P2, no matter what it is, it's the same for both scenarios. We have now both temperatures. We have the initial pressure. K we can get from the back of the book. Again, we have air. You could see it kind of stays the same throughout these pressure areas from, we're operating around, what, 400, no, sorry, 700, 800, we'll say. We're now 800 to about 1,000. So we can make an assumption that it's probably-ish 1.35, 1.34, something like that. Will it change our trajectory here? Absolutely. But since we don't have any CP data and CB data versus temperature, it's okay to make this sort of an assumption. We're going to use an average value for, say, between 800 and 1,000. Take it to be about 1.344. That's okay. Okay. So when you solve a problem, it's okay as long as you make an actual statement saying, I will assume it's between 800 and 1,000, because that's kind of what we're operating at. So I'll take a value here, 1.344. Okay. Now, in quote unquote the real world, is it true? Well, no, it's not an ideal gas to begin with. So you're making a bunch of assumptions anyway. Why not make another one? And two, let's say you want to be a little more rigorous. You could be a little more rigorous, but if you're just doing a back of the envelope calculation, that's fine too. If you're making a statement saying, I'm going to use 1.344, 1.35, or whatever it is, and you're explaining your reasoning, there's no reason for it to be wrong. It's not wrong. You're making an assumption. And so any error that you have is inherent to that assumption, as long as you're explaining it right up front. So I'm going to make an assumption. I'm going to say K, is about 1.34 because our temperature is about T1 is 1,000. And the temperature average is about T2. So we have 1,000 here and about 800 here. So, and we saw that the K around 900 is about 1.35. Something to that effect. Okay, so what I'm going to do now is I'm going to use, whether I'm using the isentropic or not doesn't really matter. Use whatever you wish. Sorry, no, you have to use the isentropic because it's an isentropic equation. So we must use T2S here. All right, so that means that I'm going to put all of that in. 765.5 Kelvin divided by 1,000 Kelvin. All of this raised to 1.345 divided by 1.345 minus 1. Okay, so this is the exponent. And it's going to be equal to P2 divided by P1. Okay, and so I don't have to convert this to SI or to whatever. Whatever the pressure is for P1, it will be for P2 because this is the ratio between them. Solve that for P2, and you get that P2, whether it's the isentropic condition or not, P2 is going to be 165.7 kilopascal, which from the Moliere, you can see kind of, it does go down, makes sense. Okay, so now we have our pressure conditions, we have our temperature conditions, and we are now asked to evaluate the entropy generation. Okay, so for the reversible process, easy. Entropy generation for the reversible is 0. For the non-reversible, that's what we're really trying to find. That's going to be a little bit of a harder thing to evaluate. All right, so if you look at the second law expression, the second law balance, the entropy balance for this system, for an open system, assuming steady state, okay, we're going to see that delta S bar is going to be equal to the summation of Q over T or for the reservoir, okay, plus the entropy generation function. This guy is adiabatic. We said that right over here. We used that in the first law. Use that in the second law. This thing's adiabatic, go away. We don't need this. There's no heat transfer. So we know that delta S is our entropy generation function. So if this is greater than 0, it's irreversible. If this is 0, it's reversible. If this is less than 0, it's impossible. So let's evaluate this thing. All right, delta S for an ideal gas, okay, is going to be the integral of Cp over T dt minus R ln of P2 over P1. We've been really assuming Cp is constant throughout. We said that in the first law right here. Cp is constant for the temperature range. So why not do it again? So we take this guy out. And if Cp is not a function of temperature, then we get that delta S bar, which is equal to the entropy generation function in this case, is Cp ln of T2 over T1 minus R ln of P2 over P1. Great. So now all we got to do is evaluate it for our conditions and see what we get. So we know that Cp is 1.14 joules per gram Kelvin. So 1.14 joule per gram Kelvin times the ln of T2 over T1. This is going to be for the actual process, not the real process. So not the reversible process. If you put the reversible process, you should get that this is 0. So put the T2A, T2 actual, T2A, okay? And P2 doesn't matter, it's the same P2. T2A, if we put T2S, it should be about 0. So T2A, we evaluated it to be 793, not this one. Again, if you put this guy, it's going to be 0. So 793.6 Kelvin divided by 1,000 Kelvin. Okay, now this R is going to give us some trouble because it's got mole in it. So let's get rid of the moles. We know it's air, so we'll be able to get rid of that really easy that way. 8.314 joule per mole Kelvin. Now I don't want these moles, but I know that 1 mole of air is 29 grams, about 28.9, whatever it is, 29 grams. And then times ln of the the pressure ratio, P2 over P1. P2 we just evaluated right up here is 165.7. P1 is given in the question is 475. It does not matter what units you use. You could use anything in the world because it's the ratio. You could use some made-up unit system because they're taking the ratio. As long as it's an absolute pressure, who cares? Same here. As long as an absolute temperature, it could be Rankine, could be Kelvin, whatever you want. Celsius won't work. Fahrenheit won't work. Degrees Newton wouldn't work. Just use Kelvin or Rankine. And here use absolute pressure, not gauge pressure, which we rarely use in our questions anyway. Okay, so 475. Oh, it's a long way to get here. Now we evaluate all of this. You can see these won't affect the units, but the mole here goes away, and we're going to get joule gram Kelvin. This is joule gram Kelvin. So our answer is going to be in joule gram Kelvin, and we get that this is 0.042. Since this thing is greater than 0, it's irreversible, which we expected. If this thing came out to be 0, something's fishy. If this thing came out to be negative, something is even fishier, because we know it's an actual process.